Hello everyone, our team is here to present our amazing work on generating realistic voice using neural and adversarial networks. So we are inspired by some of the latest advancements in adversarial network space on how voice generation using audio samples, or on how wideband speech generation task works, or on its massive applications in text-to-speech or the music generation. We aim to generate realistic audio samples which sounds like a specific person using novel adversarial network topologies, and also to use human evaluation to assess the quality of the generated coherent sentences. And how do we do that is by implementing two unsupervised neural network architectures. One is the RNN-based WaveNet architecture, and the other one is GAN-based WaveGan, which is a transposed convolution operation based on DC GAN.
So for our dataset, we utilized the LG speech dataset, which contains a bunch of short audio clips from one individual speaker, and they're already processed pretty well. And we also utilized audio speech from someone saying the numbers 0 through 9.
The examination and testimony of the expert.
1, 2. Now, the WaveNet architecture utilizes convolutional layers for both their speed and high accuracy. At every single layer, we dilate, and at the very end, we add old skip connections together to sum the output. Next slide. Each block, we take a non-linear transformation to combine those together, and then combine the earlier tensor together. And at the very end, after each layer, we do a softmax activation.
So then the WaveGan architecture is based off of a DC GAN, deep convolutional GAN, and it uses, just like WaveNet, a dilated convolutional layer instead of a fully connected one. This allows us to expand the receptive field without having to worry about training. It also uses striding for both the discriminator and the generator. However, it does use fractional striding for the generator, which basically means that you can have a lesser stride than you normally is required because you have that expanded dilated layer. They also apply batch norm to most of the layers, but they don't do this to the last layer of the generator and the first layer of the discriminator. And this is because they found that it added extra instability to the network if they did this. So this is some of the data they were able to generate. If you look at the top, that's the real data they trained on, and the bottom is the WaveGan generated data. So you can see that there's a lot of patterns that are similar to the two sets. However, the lower one, the WaveGan generated one, sounds much more unrealistic, and it is definitely noticeable that it was machine generated. Then these are the results that we were able to get with WaveNet. The top is the source audio, and the bottom is the data that's generated by our network. So as you can see, there's some patterns that it was able to develop, but it isn't particularly accurate because we weren't able to train it on a huge data set.
We used a human evaluation to rate our generated audio in terms of several parameters like coherence, clarity, and overall audio. Here are the audio samples. We asked user to rate the audio on a 5-point scale, and we received an average of 0 for WaveNet, as it was trained on a very small dataset and the produced output isn't very good to be audible. It could have been better if we used a Tacotron text-to-speech model as a supporting layer, which would feed words in the neural network to result the desired output speech like here.
This is our project audio output.
We encountered several problems while trying to generate audio, which involved getting to know how the overall audio generation works and the various parameters involved. Other problem includes creating a global phenom condition, resolving TensorFlow errors, and developing an additional architecture for neural network as they are not text-to-speech. Overall, in our project, we developed two models for speech generation, which are deep generative models, and we tune their hyperparameters for sequential generation for audio. If given further time to work on it, we would try to incorporate phenom and grammar information, multi-speaker, and text-to-speech model as a generator in GAN. Thank you.